VLSos here. This is a video lesson and optimization example. Let's imagine there's a park, rectangular in shape. And we are on a sidewalk on one side of the park. And there's a destination across the park down the way that we want to get to. This park has a size, 400 feet. And if we went straight across the park and met the sidewalk here, it would be 1,000 feet to our destination. We could ask, what is the fastest way to get to our destination? This is an optimization problem because we're asking for a fastest, an ideal time, the shortest amount of time, which will give us the fastest way to go. Now, crossing the park on an oblique and going directly to our destination is the shortest path, but we want the fastest path, which is a measure of time. And the shortest path would also be the fastest. But this is going to be a little bit more complicated because walking across the park or within this rectangle is slower than going along the sidewalk. So we have two different speeds. The park speed, or velocity, is a rate. In this case, 5 feet per second. Walking on the sidewalk is faster. We'll say it's 8 feet per second. So walking only through the park might be the shortest distance, but doing so will always be at the slower rate. We could walk around the sidewalk at our faster rate the whole time, but that path is going to be much longer. So even though we're going faster, we'll have to go a greater distance. We're going to assume that the fastest path is going to be a combination of walking across the park, but getting to the sidewalk at the ideal location so that we can finish off our walk at the faster rate and get to our destination in overall the least amount of time. That means that this situation has a geometry which is a little more sophisticated. This point right here, we could say, is the point that we meet the opposite sidewalk. And we could think that the distance of this point is going to be x less than 1,000 feet. Again, we can think of this distance as 1,000 minus x, because 1,000 feet is the distance if I had walked straight across, or we would walk straight across the park at a perpendicular or a right angle to get to that. So any closer to our destination can be thought of as closer by x. That means that we have a right triangle, and part of the path that is going to be the ideal path we can think of as the hypotenuse of that triangle and label it d sub 1. The other part of the path that will be the ideal path is t sub 2. So the total distance that is walked is going to be the sum of these two distances. What we know about d sub 2, we can write down. It's going to be the length of 1,000 minus the amount x, whatever that might be. And d sub 1 is going to come from the Pythagorean theorem as the hypotenuse of a triangle whose legs are 400 on one side and x on the other. Using the Pythagorean theorem to solve for d sub 1, I'll get d sub 1 is equal to the square root of 400 squared, or 160,000, plus x squared. But the fastest path is not going to be the sum of these two distances. We need to consider now our speeds and give them variables. The velocity along the path d1 we could call v sub 1, and that's the park speed of 5. The velocity once we get to the sidewalk, we could say is v sub 2, the velocity that will go on the distance d sub 2. And we know that to be the sidewalk speed of 8. So what are we trying to maximize or minimize? This is an optimization problem because we want the fastest path. But how are we thinking of that in terms of variables? We're going distances at a certain speed. Physics relates velocity and speed, or velocity or speed and distance with time. Or from physics, velocity is distance over time. Time is involved. The fastest path will take the least amount of time. We want to minimize time. And if we're going to optimize time, we're looking for an equation for time in terms of another variable. This relationship between velocity and distance and time can be solved for time. If I multiply both sides by t and then divide by v, I get an equivalent equation from physics. Time is distance divided by velocity. And I have distances and velocities. So the function that I'm going to minimize will be time. The time it takes to travel this distance at park velocity plus the time it takes to travel this distance at sidewalk velocity. Or time is equal to the sum of 2d over v's. Distance 1 the square root of 160,000 plus x squared over the velocity of that at that distance along that distance divided by 5 plus the distance 1,000 minus x divided by the velocity along that distance of 8. And this is an equation for time that I want to minimize or find the minimum of, and time is a function of x. I found the equation that I'm going to use the first derivative test in terms of one variable. The variable is the distance here, so if I find the minimum of the time equation in terms of x, I will have found the value of x, which will give me the place that I need to go to across the park in order to go the fastest route. I need to do a first derivative test on this function. Taking the derivative of this equation involves quotient rule, maybe chain rule, and some derivative properties. Technology can help us out. The derivative is 1/5 times 1/2 times 160,000 plus x squared to the negative 1/2 times 2x plus 1/8 times negative 1. Or, cleaning it up a little bit, x over 5 all over the square root of x squared plus 160,000 minus 1/8. Here we have the top of a radical symbol as well as a fraction bar. And this derivative, if set to 0, will find our critical points. Critical points was found with technology. And a 0 derivative was found by a calculator to be at x is equal to approximately 320.256,308. This is a case in which an approximation is appropriate. This is an important value. It's irrational, and I listed it to 6 decimal places because if we're going to use this value further in a process, then we want that accuracy, so by the end of the problem, we'll be within 3 decimal places of accuracy. Here we have a critical point, an x value. We still need to justify that it's a minimum by making a sign line for the derivative. I've labeled this point x sub 1. It's the only critical point, but it's not any value of x. It's a specific value that was previously found. So we've given it the symbol x sub 1. And on the sign line, I want to find the sign of the derivative before this value of approximately 320. I can put 0 into the derivative. And when I do, I will get 0 over 5 in the numerator of this, which will be 0. And if I subtract 1/8 from 0, I will get negative 1/8, which is a negative number. I need to put in a number greater than this critical point into the derivative, like 400. And when I do, a calculator has shown me that that was approximately 0.016, which is a positive value. So I've shown with my sign line that the derivative is negative and then positive through the critical point, where the function was decreasing, reached a minimum, and then increased afterwards. This critical point has been justified to be a minimum. It is a value of x that is a minimum of the time equation. And so it is the least amount of time for the path that crosses the park at the location x feet closer to our destination. So I need to find where this point is with x. It's going to be 1,000 minus the x value that we just determined would give a minimum time. And that is approximately, this point is approximately 679.744 feet. Now this approximation has been rounded to the nearest thousandth to give an adequately accurate answer. And because this is a contextual problem, we want to answer it in the form of a complete sentence that uses the calculated value. The fastest path across the park will be the one that meets the opposite sidewalk (679.744 feet from the destination. This is the final answer to our contextual optimization problem.